Okay, so here we're recording. So Terry, don't mind the recording, just hit that button. 8.4 intersection of lines with vectors. Okay. Where did I put my, here it is. Okay. You see that there? Okay. So you guys remember equations of lines and intersecting lines? Here's two lines where they intersect at a point, one solution. Here's another situation, two lines intersecting everywhere because they are the same line. And then you have two lines that are parallel and that don't intersect. Okay. In 3D, one more situation is introduced. That is skew lines, where there is no solution. Because in 3D space that they look like they cross on a 2D piece of paper, but really in 3D space, you could just have two lines in different directions that are skewed and they won't ever intersect. So that's kind of the fourth situation we'll encounter with the intersection of two lines. Okay. So the first three are just like what you would see in grade 9, grade 10, when you're looking at the solutions to the system of two lines. But with vectors now, that's what we're working with, vectors. So we're going to be looking at vector equations. And we're going to look at how lines intersect and what's the solution when we consider two vector equations of a line. But the goal is still the same. You're trying to kind of solve two equations to find the unknown x, y, and z. Or really, actually, what we're trying to find is a parameter s and t, so that we can produce the same x, y, and z that are common to both lines if it's a point single solution. Okay, so we'll start off with one question that doesn't jump into a solution just yet, but it just asks if parallel lines that we are given with these two equations are distinct or coincident. Okay, so when we say distinct, it means we're going to have this situation right here, distinct, where the two lines are kind of separate from each other, they're distinctively different, or they're coincident, which would be the situation we have up here, where the two lines are the same. Okay, they just may be two different looking equations, but they represent the same line. So when I look at these pair of equations, the first thing you need to look at is really the direction vector. What's happening here with the direction vector, -3, 2, and 5, and -3, 2, and 5? They're the same direction vector. Okay, so that already tells us that we're parallel. That just confirms that these are parallel lines. If they go along the same direction, they're going to be parallel. And I can make a note that here. So same direction vector. Okay, so the question is, are they distinct or are they coincident? Now, if I could find a point that's common to both lines, then they would be coincident. They'd be the same line. Essentially, any point that I take from the first equation, I put it into the second equation, it should work, and vice versa. Okay, so what points do I know from the first equation? You could try and find some if you want, but we're already given one here, one of these point vectors here, 5, -2, and -8. That's a point vector that's on the first line. So if I want to see if these two lines are coincident, then that point vector should also be a solution on the second line, right? I should be able to say that that there is a value of t. So if I put 5, -2, and -8 into the second line, that would equal -4, 0, and 2 plus t times -3, 2, and 5. If these two lines are coincident, then there should be a value of t that makes this statement true. Okay, so if coincident, there exists of t value to make this true. Okay. So really the solution to this to figure out if this works is to take out the parametric equations. So I want to write this as parametric equations. 5 equals -4 minus 3t. -2 equals 0 plus 2t, and -8 equals 2 plus 5t. And if I were to look at these three different parametric equations, take each one and solve for t, then we can see if t has the same value throughout. So solving the first one for t, I have 9 over -3 equals 5 plus 4 is 9 divided by -3 is equal to t, which is equal to -3. Okay. The second equation, -2 divided by 2 equals t, which is equal to -1. And already we can see that there is no common value of t. I'll just complete the last one for completeness here. -8 take away 2 is -10. -10 divided by 5 is equal to t, which is -2. So all three are different values of t. And you don't need, all you need is really two of them not to be the same to conclude that they're not coincidence. Okay, so my conclusion here is that therefore lines, they're not coincident. So therefore, if they are parallel, then they will be distinct. Lines are distinct. Okay. Okay. So that's just kind of like just to check if they're parallel or not, right? I mean, given a set of parallel lines, are they distinct or coincident? Example 2 jumps into more of the find the point of intersection type of question. So intersecting two lines, here are two lines that are given, do they intersect? So how do we find out? Well, again, first always check the direction vector. And I'm checking the direction vector because if direction vectors tell us that they're parallel, then a lot of the work is saved. We don't have to really be solving much. And so I look at these two direction vectors and they tell us they're not parallel. So not parallel. So direction vectors say that not parallel. Okay. So if they're not parallel, you got only two possibilities. One possibility is solution is a point. Or lines are skew lines. Okay. So what we're going to do is we're going to solve these two equations for a solution, for a point solution. And if we don't get a point solution, then our conclusion is that it is a skew line. Okay. No solution exists when you have a skew line. Okay, so solving. How do we solve? Separate, or sorry, take out the parametric equation. So let's rewrite these as parametric. Okay, so I'm going to take these equations, rewrite them as a parametric equation. So for the first one, x equals -2 plus 5t, y equals 0 plus 1t. I'm just going to write that as t. And then z equals -3 plus 3t. Okay, so that's for the first equation. I'm going to also do the same thing for the second vector equation. I'm going to rewrite that as a parametric equation. So x equals 5 minus 1s, so 5 minus s. Y equals 8 plus 2s. And then z equals -6 minus 3s. Okay, so just like solving two linear systems from a couple of years ago, you can do the same thing here. We're going to equate each parametric equation. If they're going to have a common point of intersection, then x, y, z and x, y, z should come out to be the same value. So I can equate each parametric equation. So I'm going to do that starting with the first two. So I'm going to have equate the x's here. So -2 plus 5t equals 5 minus s. Okay, so that's from equation 1. Sorry, equation x, the x component. For the y component, I'm going to have t equals 8 plus 2s. And I can do the same thing for the z component, -3 plus 3t equals -6 minus 3s. So here I am equating components. Okay, because to equate them means they have to have the same value of x, y, and z. Now you pick two and you solve them. Substitution. I could pick the first equation, and the second equation is nice already because it's already in terms of t equals something. So I could take that 8 plus 2s and substitute it for t in the first equation or the third equation, but I'll do the first equation. Okay, so I'm going to do that work down here. Move that up a little bit. Negative 2 plus 5t, and so t is going to be replaced with 8 plus 2s. And on the right side, I have 5 minus s. So the idea here is that, yeah, I'm going to substitute because I'm creating an equation with only one unknown variable, and that variable is a parameter s, and I'm going to solve for s. So expanding, and so here I'm going to write here substitution. Substitute to remove a variable, or remove a parameter, I could say that instead. And then we can start by expanding and simplifying. So here we have negative 2 plus 5 times 8 is 40, plus 5 times 2s is 10s, equals 5 minus s. And then I bring the s's to one side, so I'll bring them to the left side. I'm going to have 11s equals 5. I bring the 2 and the 40 over, so plus 2 minus 40. So 7 minus 40 is negative 33. Then divide both sides by 11, I get ls equals negative 3. So there's my value for s. Now I only created that value of s from using the x and y component. Okay, so you're gonna have to do this again. You gotta take that s and you plug it back into to find t, and I can use a second equation for that. But whatever s and t you come up with has to also work for the third equation, right? You can't just work with two equations in isolation. It has to work for all three. So I'm gonna just find t really quick here. So t equals 8 plus 2 times negative 3. And that's equal to positive 2. Okay. And so check. Check third equation. And so we're going to do that here. Negative 3 plus 3 times 2 equals negative 6 minus 3 times negative 3. And so the left side is equal to positive 3. The right side is equal to positive 3 as well. So that checks out. That works. So s and t are those values of s and t produce an x, y, z that gives us a solution. Okay. So what's the solution? You take any three of the x, y's. You take any of the x, y, z's either from the first equation or the second equation, and find your solution. So here x equals, I'll take the first equation, the first line, negative 2 plus 5t, so negative 2 plus 5 times 2, which is equal to 8. Y equals t, so that's going to be equal to 2. And z equals negative 3 plus 3 times 2, which is positive 3. So the intersect point is at 8, 2, and 3. Okay. So one more time, the solution pathway here is you start by looking at your direction vectors at the very top. Check if they're parallel. If they're not, then okay, you've eliminated two possibilities. It could be now either a single point as a solution, or you have skew lines. Rewrite the vector equations as parametric. So these are my sets of parametric equations. If they are to have a point of intersection, then the x, y, z's and the x, y, z's can be equated, which I'm doing right here. So you equate the components. You have 3 equations with 2 unknowns, so you can really only need to pick 2 of them to start off solving for S and T, which is what we're doing here on the left side, solving for S and T. But because I left the third equation alone, you got to make sure that S and T work as well in the third equation. So I'm just checking here. And because it works, then I can use S and T to determine my solution, my point of intersection X, Y, and Z. Okay. Okay. The next page, we got another pair of vector equations. Start off the same process, check their direction vectors. I see I have 2 different direction vectors. They're not scalar multiples of each other. So my conclusion, first of all, is that they are non-parallel. So direction vectors say that they are non-parallel. Okay. So again, we have a situation where, hey, maybe I could have a point of intersection, or maybe I have skew lines. So I start off again by writing the parametric equations. So I'm going to write here x equals 4 plus 2s, y equals -3 plus 7s, z equals 2 minus 1s, and then we have x equals, for the second equation, -2 minus 4t, y equals 5 plus 0t. I'm just going to write that as 5. And then z equals 4 plus 3t. So there is my set of parametric equations. And then I can equate them. So if I equate them, my x equations, 4 plus 2s equals -2 minus 4t. Okay. -3 plus 7s equals 5. So that one's a nice one. There's no t in that one already, so I can solve for s directly. 2 minus 1s equals 4 plus 3t. Okay. Now over time, as if you start doing some practice and you go, okay, do I have to write all this work? You can omit the first step where you're writing the parametric equations and go directly to where you're equating them. Saves you a little bit of time if you want. Okay, but in the beginning, it's probably a good idea to write it out, all out. Okay, solving for s. So this equation here only has s, so isolate for s. So 7s equals 5 plus 3, which is 8. And so s is equal to 8 over 7. And from there, I can solve that or substitute that into one of the other equations to solve for t. So if I take this and substitute it into the first equation, 4 plus 2 times 8 over 7 equals -2 plus or minus 4t. Okay, and then solving for t, 4 plus 16 over 7 equals -2 minus 4t. Multiply everything by 7. I get 28 plus 16 equals -14 minus 28t. And then by adding the left side, I get 38 plus 6 is 44 minus or plus 14 is 58. 58 divided by 28, -28 equals t. I think that just reduces to 29 over 14. I'll leave it as a fraction. Okay, so I have my s and t now, and that occurs from just using the first and second equation that I highlighted in yellow there. But I have to check if it works for the third equation. Okay, so here I have 2 minus 8 over 7 equals 4 plus 3 times t, which is 3 times -29 over 14. Okay, so this is my check. Check third equation. Okay. 2 minus 8 over 7 is 14 minus 8 is 6, 6 over 7. So the left side is 6 over 7. On the right side, I've got a whole mess there. It doesn't look like it's going to be 6 over 7. Negative 31 over 4. So they're not equal. Okay. So if I take an S and a T and I put them into the third equation, it doesn't work out. Then the conclusion is that there's no point of intersection. Okay, the lines don't intersect. So therefore, the lines don't intersect. And we call it skew. And our skew lines. Okay. So again, this occurs when T and S cannot satisfy all three equations. Okay. So those are all the different cases, examples of each case. So you have an example on parallel lines, you have an example on intersecting at one solution point, and now you have an example on what it looks like when they are skewed. Okay. The third example is the last example here is just an example on a little bit of an application. Okay, and it's kind of a little bit of a side thing. It's not really so much points of intersection, but rather just looking at a different kind of problem that you'll see in the practice. Determine the distance between the following pair of skew lines. Okay, so you have skew lines that don't intersect, which means there's going to be somewhere along the two skew lines that will have the closest distance to each other, right? So I can have two skew lines that spread far apart, and they can be far apart distance over here, but when they get closer, there's going to be some point where they have a very close distance. So what you have to find, what is that distance? Okay, and by definition, the shortest distance, like you may recall from, let's say, grade 10, maybe you did a problem where you had what's the distance between a point and a line? Okay, and the shortest distance, it's not this distance, it's not this distance, it's a distance that is defined to be perpendicular to the line. Okay, and this is the shortest distance. Okay. In a pair of skew lines, same idea. The shortest distance between the two skew lines is if I have a point on one skew line and another point on another skew line, the shortest distance that I could find is a line that is perpendicular to both of the lines. Okay, so you could create any set of lines between the two lines. The shortest distance ends up being, geometrically speaking, the perpendicular to both line 1 and line 2. Okay. Now to find that skew line, to find that distance rather, we're going to go back to a little bit of a thing on chapter 7 called the projection. Okay, so the projection of a vector, if you recall, is the let's do that here, another diagram on the side. So projection of a vector is if I have a vector, let's call that vector A, and here's vector B. The projection of the vector is how much of vector A acts in the direction of vector B, if that was the projection I was looking for, A onto B. Okay, and so that gives me like a little bit of a magnitude there. All right, so that idea of a vector projection is what we're going to use here. So if I look at this diagram again, if I have two known points on my lines, which we will have because we're given points on each vector, I could create a vector here like this, and I could find the projection of this vector onto the vector that is perpendicular to both lines. Okay, and that projection, because that projection is a magnitude, that magnitude represents the distance between the shortest distance between the two skew lines. Okay, so all I have to know is what is this vector from P1 to P2 to create like any vector joining the two lines, and then find the projection of that onto A, B, and and AB is going to be a direction vector, which we will find, and I'll show you how we find that. Okay, and then find that like this direction line here, and that projection just tells us the magnitude of that distance. Okay, just a quick little change here. The diagram was taken from the textbook, so I'm just going to change the numbers here for this example according to what it says in our vector equation. So this will be -1, 6, and 1. Scratch that out. And the other one will be 5, 1, and 9. Okay. So because it's from the textbook, obviously, if you go to the textbook, you'll see another example using those points that are on that picture. But I wanted to give you a different example for different set of numbers. Okay. So again, the shortest distance is represented by projection. Okay, and so the projection we're looking for is the projection of vector P1 to P2 onto this perpendicular vector. Now, this perpendicular vector is going to be the result. Well, let's call it vector n first of all. Okay, a normal vector. We usually denote normal vectors perpendicular, right? Okay, and I'll talk about how we get that vector in a moment. But just let me write the vector projection formula. So this is a magnitude. It's going to be It's going to be the vector dot product of P1, P2 dotted with that normal vector n divided by the magnitude of n. Okay, and all of that is a magnitude as well. Okay. So to get this, to fulfill this formula, to find this vector projection, I need to know vector n. And all we know about vector n is that it's perpendicular to the two lines. Okay. And so, okay, how can I find that vector if I have these two lines? Well, I'm going to look to the other thing that's given to us in this equation, and that is the two equations, and that is the direction vector of each line. So I know the direction vector of each line. I could just kind of say, well, there's a direction vector here, and there's a direction vector here. Okay, and so this normal vector is perpendicular to both these lines, so therefore it is perpendicular to both of my direction vectors. And then you think, okay, what do we know from our vector toolbox that relates two vectors and something perpendicular to both? Cross product. Okay, so I can find vector n by taking the cross product of both of my direction vectors. And you may remember the cross product of two vectors. Here are two vectors. Its cross product is going to be orthogonal or 90 degrees to both of those vectors. Now, just because on this picture it looks different because one vector is, away from the other, it still doesn't take away from the fact that my normal vector is perpendicular to both. So that normal vector, that vector has to be perpendicular to both, with the cross product. So I can use the cross product. Okay. So M1, M2. Let's cross them. I have the vectors. So let's write out here: -2, 4, and 3, -2, 4, and 3, and then the other vector 3, -2 and 4, 3, -2 and 4. Cross out 3 and 4, cross out -2 and 3, carry out that process, that procedure, cross multiply and subtract. Here we have 4 times, so the x component for my normal vector, 4 times 4, 16, take away -2 times 3, which is -6. The y component is 3 times 3, which is 9, take away 4 times -2, which is -8. And the z component, -2 times -2, which is +4, take away 3 times 4, which is 12. Okay. Simplifying this, we get a normal vector of negative of 22, 17, and -8. So that represents the normal vector, perpendicular vector between L1 and L2. Okay. Before you say, okay, sir, what do we need? Can we just take the magnitude of that and we call it a day? No, because that vector does not necessarily mean it goes from point A to point B. That could still be a vector that goes like this, or maybe it's a vector that's shorter, okay, which is why we need the projection. So the projection of this vector along the direction of this normal vector, okay? So if you were to go, if I find the magnitude of this, that's the solution? No, may not necessarily be the solution. It could be, it could happen by coincidence that it could be, but don't rely on that. Okay, so we still do, despite saying that, we still do need the magnitude. So the magnitude of n to help us with the vector projection formula. The magnitude of n is the square root of 22 squared plus 17 squared plus -8 squared, which is the square root of 837. Okay. Okay, so we have that. We can go back to our projection formula and say, okay, P1, P2 dotted with n. You got to use the algebraic dot product. So I'm going to take each component, the x component of P1. Oh, we never created P1, P2. Oh, I forgot about that. Okay, let's do that now. P1, P2. So creating a vector connecting those 2 points. So we got, what do we have? 5 minus -1, 1 minus 6, and 9 minus 1, which is 6 for the x component, -5 for the y component, 8 for the z component. And then we can now take the projection of P1, P2 onto n. And that would be P1, so the algebraic dot product here, 6 for the x component multiplied by 22 for the x component of n, plus -5 for the y component of P1, P2 times 17 for the y component of n, plus 8 for the z component and -8 for the other z component. Just gonna move this over a little bit so it's not. There we go. And then I divide that by the magnitude of n according to the formula in red. So the magnitude of n is square root of 837. And it's going to be the magnitude of all of that. Okay. And so you find that if you simplify the top, we get 17. And the bottom is square root of 837. Both are positive, so we're good to remove the absolute value sign there. And I'll just say units. If there were units, you could put the units in, but I'll just say units. So the magnitude, or the shortest distance between the two skew lines, is a number represented by 17 divided by the square root of 837. Okay. So this is kind of like a question that encapsulates all of it, right? You got to know how to do your dot product, you know your cross product, vector projection, and you're applying it to the concept of skew lines. Okay. All right, that's 8.4. Any questions? Okay, I'll give you some time to work on the some of those practice problems, and I'm going to stop this video. Like and subscribe, everyone. Okay, there you go.